Hello students, so welcome back to the lecture of the chapter solutions. So this will be the theory part 6 continuation. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. Please note that parts of the content may have been generated using generative AI, which is experimental. So we have already covered this objective in our previous classes. Today we will learn about the abnormal colligative property, which are exhibited by some of the solutes, and we will see that why there is a deviation from the calculation that we have. So the problem was of the abnormal molar mass. As I have told you already, that colligative properties are dependent upon the number of particles. Okay, well and good. It is not dependent upon the nature of particles, right? So, what is the problem with the ionic compounds now? So, when you are say dissolving one molecule of KCl, so when we are considering its concentration, we are considering KCl as one molecule. But is it true? Of course not. When it is dissolved in your solution phase, you will get two ions out of the KCl, so this electrolyte, okay, which are K plus and Cl minus. Therefore, we can say that from the same one molecule, we have two different constituents. Now, this creates a problem. Our fundamental base was that the number of particles is the main deciding factor for the calculation of colligative property, and we are changing the same by dissociation. Now this should be taken into consideration to calculate the values more properly. Now, as I said, as a consequence of this, if we ignore the inter-ionic interaction, then 1 mole of KCl will give, in 1 kg of water, will give double the expected value. Okay, since there are now two particles, therefore if the expected value of elevation in boiling point was 0.52, it will be now 1.04 Kelvin. And when this value of elevated boiling point is taken and we calculate the molar mass experimentally, then it will deviate from the value which is being calculated without considering the I. So for Hindi classes, you can visit our website. We have the Hindi version of the same lecture there. Okay, it will be uploaded in one day. I would say that it will be there tomorrow. So consider the ethanoic acid. So previous example was of dissociation. This is of association. In this, what will happen? 2 moles of ethanoic acid, which is also called as acetic acid, will dimerize. It will be dimerized to form a single entity in the benzene, and it is happening due to hydrogen bonding. Now, this will decrease the number of particles. Of course, if you have dissolved 2 molecules of acetic acid, but in the solution phase, we have only 1 molecule as a whole. And it is happening due to dimerization. So this is the equation that shows. So dimerize means to associate 2 molecules. If it is trimerization, then it will associate 3 molecules. So 2 molecules will give 1 mole of this CH3COH whole twice. This thing can be showed here with the help of this diagram, where we have a hydrogen bonding between the first ethanoic acid and our second ethanoic acid. And this is the hydrogen bonding interaction that I am talking about. Is it clear? So it's very, very important to understand that both of the association and dissociation changes the value of colligative properties that we are calculating. Now, it can be said undoubtedly that if this association or dissociation will happen, then delta TB and delta TI will change. Like in this case where there is association, the normal value that we will get will be half of the original value. Okay, means in the calculation we will get half of the original value, and such a deviation is called as the abnormal molar mass. So this was all about the abnormal molar mass in a qualitative manner, but to understand it more efficiently, you must note that what is the thing that is being going on. So Ojas, association means, if you think of it in a simple way, so suppose you take two pieces of paper, right? Just apply glue on each of them and you keep them with your palm in one side. Okay, just keep them on by layering them together, then they will stick. So there the force of interaction was your sticky thing, which was glue. Similar to that, if you are doing association of this, say, acetic acid, then here what is happening? Here two molecules of acetic acid are coming together, and here the force of interaction is hydrogen bonding between the doubly bonded oxygen of ethanoic acid of one molecule and the hydrogen bonded oxygen bonded hydrogen of the other ethanoic acid molecule. So this is the interaction that I am talking about. Okay, and the opposite case will be of dissociation, where you suppose if you are taking KCl, so KCl is ionic in nature. So whenever you dissolve it in a polar solvent, it breaks down into two parts, which is K plus and Cl minus. Now this abnormality was being controlled, or you can say being quantified, with the help of the Vent-Off factor I, and it was there to account for this extent of association and dissociation. Got it? So the whole big picture is that what we were having, what difficulty we were having is that the case of association and dissociation was disturbing the number of particles, and hence we were not getting the actual value, and there is a deviation in the calculated value and the observed value, because all of these colligative properties are totally dependent upon the number of particles. Okay, so to counter that, this I factor was introduced by Vent-Off. Now how it is defined? It's very easy. Suppose if you are taking any substance, then of course it will have a molar mass, so that is taken as the normal molar mass, and the ones which you have calculated using your calculation, okay, without considering the association and the dissociation, it will be called as the abnormal molar mass, and their ratio is termed as I. So this is one definition. Second definition would be observed colligative property. Okay, so if you do not consider the association and the dissociation, you will get the calculated one and one which you are getting it experimentally. So the experimental colligative property divided by the calculated colligative property. And last one is number of particle after dissociation and number of particle before dissociation. So these three formulas can be applied to calculate the I. So if you are talking about suppose KCl, so before dissociation, how many number of particles were there? 1. Okay, total number of particle was 1. After association or dissociation, it means 2. Yes, observed means experimental. Yes, right. So observed means experimental. Both terms can be used. Okay. Now these are the three definitions of your Vent-Off factor I. You will, when you will do questions, then you will get much more great idea about this. So it's very easy to understand once you start doing questions on it. Okay. So don't worry if you are having issue till now. I will try my best to solve it through the question. Okay. As I said, that the abnormal molar mass is the experimentally defined. Okay. Abnormal molar mass is the experimentally defined value, and calculated colligative property is the one which is obtained by assuming that non-volatile solute is neither associated or nor dissociated. Now in case of association, I will be less than unity. What is the meaning of this? I will be less than unity means the value of I will be less than 1. So if you take the case of association, then the number of particle before association will be greater, because initially we have one ethanoic acid and now we have two such ethanoic acid joined together. So 2 are the initial one and 1 is the final one. So therefore the number of particle after association is less. That means this value is smaller and this value is greater. So that will of course give you an I value which is less than 1. For example, if we take the case of KCl, the KCl was dissociating into 2 parts, therefore I will have a value which is very close to 2. So due to some interionic interaction, this value may be deviated in a small decimal manner, but it's okay to consider it as 2. Whereas the value of this I for ethanoic acid will be nearly 0.5. Again, there will be a very greater deviation from this dimerization, as this dimerization occurs to a larger extent but not wholly. Okay, so it will be closely related to this value which is 0.5. Yes, we will see more examples of association in our question part. Now what will be the formula? What will be the new formula? It's very easy. Just use this thing. Okay, I've calculated all this formulas of our new calculation using this ratio. So observed colligative property is equals to I multiplied by N2 by N1. Okay, so this is your new formula now. You just have to multiply our initial formula by I for the case of relative lowering. Similarly, for elevation in boiling point, it will be delta TB into I kbm. For the delta TF, it will be I kfm. And for osmotic pressure, it will be pi is equals to N2 RT by V. So we have just multiplied our initial formulas with I. I hope you are getting this point. If you have a doubt, you can ask it now. With these formulas, it's very easy to understand if you are aware about the previous formulas. Now let's see the values of I for some ionic compounds like NaCl, KCl, MgSO4 and K2SO4. So here is a list of that. NaCl will broke down into 2 parts. What are those parts? It will be 2.00. Why I'm taking it as 2? Because NaCl dissociates into 2 parts. So you can see it very clearly that we are moving from 1.87, 1.94 to 1.97. So what are we doing here? See, the value of I for NaCl is always taken as 2, right? It is taken as 2, but this value is the ideal value. In your calculation you will take 2, no problem with that, but in actual sense, if the concentration is high, you can see that at a higher concentration like 0.1 m, you have a value which is at a greater distance from the ideal value. As we go on decreasing this concentration, our value become close to the ideal value. And why it is happening? It is happening because in case of higher concentration, there is a chance of interionic interaction. So at last, Na plus and Cl minus are oppositely charged. If you take a high concentration, that means you are taking a large number of molecules in a smaller area. So that is the basic idea behind concentrated solutions, right? Now, if they are close to each other, they may attract each other also. That will result in somewhat deviation from this complete dissociation value, which is 2. Now, as we increase this, say, concentration, the value get on moving away from this ideal value. Yes, what's your problem, Brata? But as we decrease the concentration, it will move closer to this value of 2. Now, same thing can be seen for KCl, MgSO4 and K2SO4. Your KCl also dissociates into 2 parts, K plus and Cl minus. Same for MgCl, but K2SO4 dissociate into 3 parts. What are those 3 parts? So there will be 2 K plus ions and 1 SO4 2 minus. So you, for the notes, you can just rewatch this video on YouTube. So it is there, okay, and you can make notes by your own, or else you can visit our website also. There is a link for the same. So it's very, so coming back to this, yes, saying it right. So it will be 2K plus and 1 SO4 2 minus. Manpreet, for Hindi version of the same say lecture, you can visit our website. It is there in the website, the same lecture in the Hindi version. Okay, very well. Now from here we can get 2 things which are very, very important, and there is a very good question in the example regarding the same thing. What is that concept? So as you keep decreasing the concentration, the value of I becomes closer to the ideal value. Like for a lower concentration like 0.001, it is 1.97 for NaCl, 1.98 for KCl, 1.82 for 2.00 for MgSO4, and 2.84 for 3.00. Okay, so this I is your Vent-Off factor, and it is simply the number of particles in which your substance is dissociating. But if you take a lower concentration, a higher concentration, then you will see a much more deviation. So it is 2.32. There is approximately a difference of 1.7. Okay. Similarly, for MgSO4, there is a differentiation of 0.80. Got it? Moving on further. Now, let us take the case of dissociation if the dissociation is not occurring to 100% extent. Now, what is it 100% extent? So, for some molecules and for some electrolytes, it is seen that there is not complete dissociation. Okay, they are partially dissociated. And for the cases of some molecules, there is partial association also. Like if we take a hypothetical example where we have the association of a molecule A, and suppose n number of A molecules are associating to give us a closed entity which is represented by writing AN. Got it? Now remember, it is happening in a way that there is a partial association. Now if we consider alpha as the degree of association, then we can write number of associated particle as 1 minus alpha. So we have just used our equilibrium knowledge to do this. So initially if there was 1 mole, then alpha number of particles have dissociated and form this AN. So our concentration after association will be, or the number of unassociated particle after association will be 1 minus alpha. Similarly, what will be the number of associated molecule? It will be alpha by n. Therefore, the number of effective moles will be 1 minus alpha plus alpha by n. Just add these two things. So these are the total number of effective moles after association. Then what is the value of I? So we have seen the formula for I. Total number of particle after association divided by total number of particle before association. So before association there were one particle only. Now we have 1 minus alpha plus alpha by n. So this is the value of I. If you rearrange it, you will get it as alpha is equals to I minus 1 by n minus 1. Okay, so what is the meaning of effective? So let us try to understand this whole thing in a much more detailed manner. Suppose, say we take the case of acetic acid. Okay, so we have taken the example of acetic acid initially, and we have seen that it was dimerizing, means two molecules were coming together and forming one single entity. Very well. So what we can say, if we divide this whole thing by 2, then we will get 1 by 2, right? Now, initially, if we take the case of initial circumstances, so initially there was one molecule. Then, here we have 0 number of associated molecules, as there was no initiation initially when we have just introduced this acetic acid into benzene. Remember, we were doing the association in the benzene solvent. Okay, so before this introduction of this acetic acid into benzene, one molecule was present, right? Now after we dissolve, or after equilibrium, I would say, or more appropriate word will be at equilibrium, what will happen? Alpha amount of, say, CH3COOH will associate to form alpha by 2 molecules. Is it clear? Since half is the, say, your stoichiometric coefficient, so I have divided this alpha by 2, because one particle will form half product, therefore alpha particle will form alpha by 2 product. That will give you the total number of particles. So it's very simple to calculate the total number. Just add this value and this value. It will give you 1 minus alpha by 2. What was the initial number of particle? It was 1. What is the final number of particle? It is 1 minus alpha by 2. Therefore, I is equals to 1 minus alpha by 2 by 1. So in this way you will do it. Okay, I think now you should be able to understand it in a much more better way with the help of this example. Moving on to the case of dissociation. So suppose the same molecule which was associating earlier is now dissociating. So it's not a perfect case, it is just an ideal case that we are considering here. So suppose we take a different molecule. Say we take a different molecule which is again represented by A, and this A is being associated is being dissociated into n moles. So this is dissociation. Okay, so this is dissociation. Then what will happen? One particle is initially there, but after this dissociation, alpha particle will be removed and the same n alpha will be formed. As one particle is getting dissociated into n number, therefore alpha will be dissociating into n alpha. Then what will be the number of particles at equilibrium? It will be simply 1 minus alpha plus n alpha. Then I can be calculated as 1 minus alpha plus n alpha by 1, which will finally give you the alpha value as I minus 1 by n minus 1. Now remember these two formulas, it's very important. For the case of association, it is I minus 1 by n minus 1. Whereas in case of dissociation, it is I minus 1 by n minus 1, where n is the number of particles getting associated, and in this case it is getting dissociated. So it's not always alpha 1 plus alpha by 2. Okay, yeah. So 1 minus alpha plus alpha by 2. So that will give you 1 minus alpha by 2, I think. It's true, right? So this is the calculation. It will be 1 minus alpha by 2. Now this is a question for you. You can try it by yourself. If not, then I'm telling you the solution also. So the question says that we are taking 0.6 ml of acetic acid, which is having a density of 1.06 gram per mole. Then it is dissolved in 1 liter of water. The depression in freezing point was 0.0205. We have to calculate the Ventov factor and the dissociation constant of acid. How we'll do it? So number of moles of acetic acid will be how much? We know the volume, we know the density. We can calculate the mass easily by multiplying both of this. Then given mass by molar mass will give you the number of moles. So this is the thing that we have done here for the acetic acid. So first we have calculated the number of moles. Then we have calculated the molality, which is number of moles divided by the mass of the solvent in kg. Now since our solvent is water here, its density is always 1 gram per ml. Okay, so we have converted this 1 gram per ml to liter by multiplying it by 1000. Okay, so we get it here. So we have converted it into gram, okay, not liter, into gram by multiplying it by 1000. We got 0.0106 mole per kg. Now using our equation, we can calculate our delta TF, which will be 1.86, the KF value, multiplied by the N value, okay, which will give you, not the N value, the molality value, which will give you 0.0197 Kelvin. So this is your delta TF. So it was told earlier, I guess, that for the formula of depression in freezing point, we take molality, not the molarity, always. Now what will be the value of I? It will be observed freezing point divided by calculated freezing point. So this is the calculated one, and this is the observed one, 0.0205. So why we have taken 0.205? Because the depression was given as 0.205. So this will give you I value as 1.041. You can easily calculate the difference in the freezing point from this value by subtracting it from 0. Okay, we don't have to worry about unit because delta TF value is a difference thing, and in difference we don't consider the unit in case of temperature. Once we got our I, we can easily calculate the dissociation constant. So how we'll do it? Initially we have n moles. It was H plus was 0 and the acetic acid is also 0. But after dissociation, suppose X is the degree of dissociation, then it will be n into 1 minus X, the dissociation, and it will result in nx moles of H plus and nx moles of acetic acid. Then what will be the total number of X? No, X can never be negative. So what will be the total number of particle? It will be nx plus n into 1 minus X, that will give you n into 1 plus X. Now I is being already calculated here. If you put these values here, so n will be 2 in case of acetic acid, as 2 particles are getting dissociated from one particle of this acetic acid. So if you take the value of n as 2 and try to calculate x from here, if your I value is 1.041, then you will get your x as 0.041. But we are interested in the dissociation constant. So dissociation constant will be the concentration of H plus multiplied by the concentration of acetate ion divided by the concentration of acetic acid. So this is a direct result from the dissociation. Since we know the value of n and x, we can calculate each of this value, nx, nx and n into 1 minus x, which is being done here. Finally, the Ka value will be the product of the concentration of the products divided by the product of the concentration of the reactant. Yes, your x is your alpha here. Same alpha is taken as x in this case. So that will give you 1.86 into 10 to the power minus 5 as your final Ka value. So this was our theory part. Now we will see some exercise questions of the NCERT. Okay, now we will do some NCERT exercise of the chapter solutions. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So this is our first question. In this, what we have to do? The question says that a solution of glucose in water is labeled as 10% weight by weight. Now, what would be the molality and mole fraction of each component in the solution if the density is given as 1.2 gram per ml? Also, what would be its molarity? So this is your question, okay, and it is the question number 1.5 from NCERT. So let's see how we can solve it. So you have 10 seconds to just think over it, then we will start the solution. Now, let us see the solution. The question is asking to calculate the molality and mole fraction from this weight by weight percent, and we have to also calculate the molarity if your density is given as well. How will calculate it? By 10% weight by weight, it means that 10 gram of glucose is dissolved in 100 gram of the solution. So for partial association and partial dissociation, the formula goes like this. So it will be alpha is equals to I minus 1 by n minus 1. So this is for dissociation. Okay, this is for dissociation, and for association it is, so if I represent say association by beta instead of alpha, it will be I minus 1 by 1 by n minus 1, where n is the number of particle dissociated, means how many particles are being produced after, so number of particles after dissociation, and here the number of particles getting dissociated, getting associated, okay, getting associated. Yes, the chapter is over. So now it is good. We got the formula. So coming back to our question, it is being written that it is a 10% weight by weight solution, by which we can say that 10 gram of glucose is dissolved in 100 gram of the solution. Now, if 10 gram is glucose out of 100 gram, that means it is simple to say that 90 gram is water. Then our next goal is to calculate the molality. For that, we need the number of moles of the glucose. So for that, we have calculated the molar mass, which is 6 into 12 for carbon, 12 into 1 for hydrogen, and 6 into 16 for oxygen. So it will give you 180 gram per mole. Now what will be the number of moles of glucose? It will be given weight by molecular weight. So we have already seen that if it is 10 by 10% weight by weight solution, then we have 10 gram of glucose in 100 gram of the solution. So 10 gram of glucose means the given weight is 10. What will be the molar weight? It is 180. So if you divide both of this, you will get the number of moles of glucose as 0.056 moles. Then coming on to the molality of the solution. So molality formula is number of moles of solute by mass of the solvent in kg. So mass of the solvent was 90 gram. We have just converted this thing into kg by dividing it by 1000. That will give you 0.09 kg. So the molality is 0.62 m, small m. Our next target was to calculate the mole fraction. For that, we would also need the number of moles of water. So we know that the mass of water is 90 gram. Therefore, moles of water will be given mass by the molar mass. It will give you 5 moles as the number of moles of water. So we have the number of moles of glucose and the number of moles of water. Then we can easily calculate the mole fraction. It will be the moles of glucose divided by total number of moles, which is 5 plus 0.056. If you calculate this value, you will get this value as 0.011 as the mole fraction of glucose. Now since it is a binary solution, then the moles of water and the moles of glucose are the only particles that are present there. Hence, the mole fraction of water will be 1 minus chi of the glucose. So for binary solution, we know that the summation of all the mole fraction is 1. Okay, this is true for all kinds of solution if you consider more than 2 components also. But since it is a 2 component thing, then we can calculate the other mole fraction using this simple formula. No, we cannot neglect it for the glucose as this value is not that much small. Okay, it is comparable in with this 5. Okay, so we have to take this. You can't neglect this value. So if you just subtract 0.011 from 1, you will get it as 0.989. So we have calculated 2 things here. First is molality and second is mole fraction. Now we are interested in molality, for which we will need the volume. And for volume, we can go and check out this density. So let's see how we can use this density to calculate the volume. So if you have to calculate the volume, we must know the formula is density is equals to mass per unit volume. So if density is 1.2 gram per ml and the mass is 100 gram, therefore volume will be mass by density. Very easy. So we got this value as 83.33 ml. But for the molarity, we need the volume of the solution in liters. So to do this, we have multiplied the milliliter thing with 10 to the power minus 3. So we got the value in the liter. Then what will be the molarity? It will be number of moles divided by the volume of the solution in liters, which is 0.67 capital M. So in this way we can calculate the molarity. So this is a very good question to get a grasp of all the ideas related to concentration terms. Okay, so that is the reason I have picked this question. I hope this thing is clear to you. Moving on to the next question. Next question says that the vapor pressure of water is 12.3 kilopascal. We have to calculate the vapor pressure of 1 molar of a non-volatile solid in it, and the temperature is 300 Kelvin. So you have some time to think over this question. Your time starts now. Okay, let's see how we can solve it. So two things are given here which are important. First is the vapor pressure of water. So this vapor pressure is of pure water, and the molality of the solution. How we will do it? Before moving on to the answer, let us analyze that what is given. So it is given that 1 molar solution is the concentration. Then it means that 1 mole of the solute is present in 1000 gram of the solvent. So it's very simple thing to derive from the given value of molality. But we know that the molar mass of water is 18 gram per mole. From here we can calculate the number of moles. But why are we calculating the number of moles? Because this is a case of relative lowering, and for the relative lowering we know that it is related to the mole fraction, or I would say more appropriately it is related to the ratio of the solute moles to the solvent moles. Got it? Is it clear? So, because we have neglected the solvent there in the derivation part. So if you calculate the number of moles in 1000 gram of water, it will be 1000 divided by 18, that is 15.56 mole. Then coming on to the mole fraction, if we don't neglect the water, the solvent, then we can also do it, but here we are considering it, right? So if it is 1 molar solution, it means 1 mole is dissolved in 1000 gram of water. So number of moles of the solute is 1, and the number of moles of solvent, which is water, it is calculated here, it is 55.56. If you put all these values, you will get 0.017 as the mole fraction of the solution for the solute. Now coming on to the given data of water, which is vapor pressure, it is 12.3 kilopascal. So it is for pure water. We know this relation. It is P01 minus P1 by P01 is equals to Chi2. So this is relative lowering of vapor pressure. If you put all these values here, so Chi2 is being calculated. P01 is given 12.3. So this will give you P1, which is further calculated as 12.3 minus P1 is equals to 0.2177. So we have just multiplied this thing here. Finally, your P1 value will be 12.08 kilopascal. Okay. So I would say that you can expect such calculation in some questions. I would say nearly 1 to 2%, but it is not factual for all of those questions. Okay, so don't have to worry, because if it is lengthy, then it is lengthy for all of the students that are attending the exam. Okay. Now, moving on to the next question. Next question is, we have to calculate the depression in freezing point if 10 gram of this given compound is dissolved in 250 gram of water. So it is 1, 2, 3. So if you just try to name it, it's 1, 2, 3, 4 butanoic acid. It is 2 chlorobutanoic acid, right? So if you are adding say 10 gram of this compound into 250 gram of water, then we have to calculate the depression in freezing point. The value of Ka is given here and the value of Kf is given here. So in this case, you have to consider the association and the dissociation thing. So you have 10 seconds to solve, or you can say you can think over this question for some time. So just try to understand that what is happening. Yes, it will dissociate as the dissociation constant is given, right? Let us move to the answer now. So we have given with two things. First of all, the mass of the compound which is dissolved in water and the amount of water in which it is dissolved, it is 250 gram. Then the dissociation constant and the Kf value are given. So let's see how can we solve it. First of all, we'll calculate the molar mass. It's very simple. You can just look over this calculation. It's very simple to understand. It will be 122.5 gram per mole. So this will be the molar mass. Now the number of moles will be the given mass by molar mass. This value will come out to be 0.0816 mole. Now it is being said here that this amount of, or this moles of this compound are dissolved in 250 gram of water. Then we can calculate the molarity also from here. So number of moles by the mass of the solvent in kg. So to convert this 250 gram into kg, we have divided it by 1000. From this we can get the molarity as 0.3264 mole per kg. Now further what we can do, we have calculated the molarity. We will move on to the calculation of alpha. Since our acid is getting dissociated, it can be represented by the equation. So initial concentration is suppose C, okay. So after some time it will be dissociated. So C minus C alpha, or C into 1 minus alpha, which will give C alpha of this anion and C alpha of this cation. Then Ka can be written as the product of the concentration of the products divided by the product of the concentration of the reactant. So we have one reactant only. So we have written this thing in the denominator and C square alpha square in the numerator. If you just simplify it further, it will be C alpha square by 1 minus alpha. Considering the Oswald dilutions law approximation, we have neglected 1 minus alpha to alpha, okay. Sorry, 1 minus alpha to 1. So this will just substitute 1 minus alpha with 1. That will give you K is equals to C alpha square. So from here you can get your alpha. Alpha will be root under K by C. So K value is given here. So if you do this, you will get it as 0.0655. So I've shown all the calculation related to it so that you can get a revision of the equilibrium thing also. Now what we will do, we have the Ka value now and the alpha value also. Then again we can say for the dissociation 1 0 0. So I am doing the derivation, or you can use the formula also that I have told you earlier, which is alpha is equals to I minus 1 by n minus 1, or you can do the whole process which is being done here. So initially it is 1, okay. So it is 1, 0 and 0. After some time it will be 1 minus alpha, this will be alpha and this also will be alpha. What will be the total number of moles? It will be 1 minus alpha, this will, anion will be also alpha and this cation will be also alpha. So just add all of this, you will get it as 1 plus alpha. Therefore I will be what? 1 plus alpha, which is the initial number of particles after dissociation, and particle before dissociation it was 1. So 1 mole was getting dissociated into these parts, right? So before dissociation or before dissociation it was 1 in case of this acid, and after dissociation it is 1 plus alpha. So this will give your I. We know the value of alpha which was calculated earlier. If you add both of this, you will get it as 0.655, 1.0655. Hence we can say that our depression in freezing point can be given as delta TF equal to IKFM. We have seen the revised formula earlier also. I value is being put up here, KF value is given in the question, and molality value was calculated earlier, which is 0.326 per mole per kg. Therefore, the final value will be 0.65 Kelvin. So, is there a problem till now? You can ask. Okay, let's move further. So our next question is, benzene and toluene, they form ideal solution over entire range of composition. So first thing is being written here. It means this will follow the Raoult's law. No doubt with that. Now, the vapor pressure for the pure benzene and toluene at 300 Kelvin is given as 50.7 mm of Hg and 32.06 mm of Hg. So you have to calculate their mole fraction in the vapor phase if we are dissolving 80 gram of benzene in 100 gram of toluene. So you can think over this question for a small while. Then we'll move to the solution. So vapor pressure is given for the pure solvents and solute, and their concentration is also being given in a way if you look at this values, which is 80 gram dissolved in 100 gram of toluene. So what is the first thing that we are interested in? If we consider the vapor pressure, so we are interested in the mole fraction. For that, we will need the molar mass of benzene. You can calculate, this value will come out to be 78 gram per mole, and molar mass of toluene will be 92 gram per mole. Hence, number of moles of benzene will be given mass, which is 80, divided by the molar mass, which is 78. It will give you 1.026 moles. Similarly, for the case of toluene, it will be given mass, which is 100, by molar mass, which is 92. This value will give you 1.087 moles of toluene. Then further, which is the solute here? It is a very good question to think of. So solute is your benzene, as its moles are less. Hence we can calculate the mole fraction of this benzene, which is 1.026 by total number of moles. If you do this calculation, you will get this value as 0.486. Now what about the mole fraction of the toluene? It will be simply 1 minus 0.486. It will give you 0.514. Now we are interested in calculating the vapor pressure of the benzene in the vapor phase. How we'll do it? So we know that the pure solvents, which is benzene, its vapor pressure is given as 50.71 mmHg. Similarly, for toluene, the vapor pressure will be 32.06 mmHg. What will be the partial pressure of benzene then? We know the formula from the Raoult's law. It is chi b into P naught b. If you calculate this, you will get it as 24.645 mmHg. Similarly, for toluene, you will get the vapor pressure of toluene as 16.479 mmHg. What is the mole fraction of benzene in the vapor phase given by? It is given by the pressure of benzene in the vapor divided by the total vapor pressure. So total vapor pressure will be addition of both of this, and the vapor pressure of benzene is 24.645. If you put these values, you will get the vapor pressure of the benzene in the vapor phase, which is 0.6. Then moving on to the next question. The amount of CaCl2 dissolved in 2.5 liter of water is to be calculated if the osmotic pressure is 0.75 and the value of I is 2.47. So again, it's a very easy question to do. How we'll do it? So you have 10 seconds to think over it. Okay. Now let's see how we can solve it. So first of all, two things are given, value of I, okay, and the concentration thing, and the osmotic pressure also is given. So why I am saying it is as concentration? Because we have a partial thing that is required for the concentration, which is volume. We know that pi is equals to CRT. The new improved formula would be pi is equals to ICRT. Or we can say pi is equals to I multiplied by weight of the solute by the molar mass of the solute divided by the volume multiplied by R into T. So here we are calculating the molarity. So pi value is given as 0.75 in the question. And volume is 2.5 liter. Okay. And the I value is 2.47. So we have to first convert this temperature thing into Kelvin, which is 300 Kelvin. R value in terms of liter ATM per Kelvin per mole is 0.0821. Then what is the molecular mass of this, say, our CaCl2? It will be 111 gram per mole. So it is simply calculating by considering their atomic weight. Therefore, weight would be calculated in this manner. Just put all these values. You will get it as 3.42 grams. Therefore, the total amount which is required is 3.42 gram. So this was all for today's lecture. Thank you.